अस्सलाम वालेकुम डियर स्टूडेंट्स। तो आज का जो हमारा लेक्चर है दैट इज अबाउट energy momentum tensor of electromagnetic field, right? So in one of my classes we have discussed that what is that energy momentum tensor. Now we need to discuss again that energy momentum tensor of electromagnetic field, right? So you might remember that if we have this the action for this electromagnetic field, the action for the field can be written as so action for the field we can write as that's SF. So that's equal to minus 1 by 16 pi du, right? Okay, and this is our this LK. It is our this electromagnetic field tensor, and this du omega is it is that CDT dx dy and dy, right? So it's a four-dimensional space. You are writing that definition for that. And this is our electromagnetic field tensor. So you know that, and so this, if we talk about this electromagnetic field tensor, because what I am saying that if we write that we can this electromagnetic field tensor, I can write it in terms of that the determinant of that electric as well as magnetic field components, right? तो इसके पहले मैं लिख सकता हूँ. So I can also show prove that this F mu nu or F mu nu this is invalid, so this remains invalid, right? And this will be a scalar because, right? So the product of this these two electromagnetic field tensors, one covariant and another contravariant. So this is purely that scalar, right? So this is a scalar, and instead of that, if you write now in terms of that epsilon I j k l f I j f. So this also remains invalid. But there's a difference when you multiply by this. This is in one of the lecture I already told you about this Levi-Civita and it has that property that it can have plus one when it follows that these indices follows the cyclic order, or if it is anti-cyclic, this ijk. So this the value of this epsilon it will be equal to minus one. Or if there's a repetition, अगर यहाँ पे indices में लिखूंगा, if it should be iikl, right? So that epsilon will be 0, right? Because we know that we have that epsilon 1, 2, 3 equal to epsilon 2, 3, 1, that is plus. And we can have that epsilon 1, 3, 2 equal to epsilon 3, 1, 2, that is minus. Okay? And epsilon 1, 1, 2 will be equal to 0. So this is the property that it has when there's a cyclic order, so it will be plus 1, or if it is anti-cyclic, it will be minus 1, or if there's a repetition of these indices, so its value will be equal to 0. But this is our this epsilon, this is our antisymmetric unit tensor. So this is our antisymmetric unit tensor. Right? But this is again a scalar. But this scalar, it's not pure scalar, it is pseudo scalar. Right? So scalar, you understand, like we have that length. If we transform this from one inertial frame to another inertial frame, so it remains invariant. Right? So it's scalar quantity, like we have that length. So length remains invariant when you go from one inertial frame to another inertial frame. And but this it's a pseudo scalar. It's not pure scalar. Right? Now, if you write now, so this, if you write this f mu nu here, so that means this can be a complex quantity, right? So this will be that f mu nu. So this will be equal to that. It will be equal to e square minus v square. So that means this f will be equal to. So it will be some e plus iota b, right? So because that contravariant has that minus a, e and b in our previous lecture, I already told you. So the components of that, if you have the contravariant of this electromagnetic field tensor, so it is components will be like, if we have that f mu nu, right? So it is components will be minus e and b, and if you have that f covariant, so this will be that e and right? So when you take the product, so this will be a square minus b square, okay? And this product remains invariant, right? So that means if you transform this tensor from one inertial frame to another inertial frame, so this remains invariant, e square minus b square, right? So in addition to that, we can have this. So that means this is purely in this three-dimensional form, right? So we can have that e dot h also, or e dot b, e dot b. So that's also invariant. So this also, because this is simply the scalar product between that electric and the magnetic field components, right? So this also remains invariant. Okay, right. Because this is our that polar vector, and that's our action vector. Okay. So that means the product between, so polar, when you transform it from one frame to another frame, so it will go from e to minus e. It changes the sign, another transformation. But this b is, it's an action vector, but so b remains invariant, right? So overall e dot b remains invariant. Okay. Now, so in order to, because otherwise, if you talk about now, if you write now this one, okay. So this remains invariant because this e changes sign under transformation. Okay. So let me write it here. Uh, okay. So because this e dot b remains invariant, but because e will go from this, because e will go from e to minus e, right? And b goes from b to b, right? So when you make the transformation from one inertial frame to another, but so e dot b remains invariant only. So when you take the square of that, so this quantity remains invariant. Okay. So this quantity e dot b square remains invariant, right? Okay. So that means if we have this electric, so what we conclude from here? So that means if we have in one frame, if you take first frame, अगर एक frame लेंगे जहाँ पे electric और magnetic field है, H, or you write sometimes B. Okay, so let me write it here. So E and B. So these are at right angles in one first frame. So this remains same in the other frame. So they will be at right angles in another frame of axis, right? Or you can say that this, because when these are at right angles, so E dot B equal to 0, right? So you can say that this E dot B will be 0 in first frame, right? So this will be true for other frame of reference if you transform it, if you want to calculate this in another frame, right? Or you can say that uh, if this value of this, absolute value of this is equal to this one. So the absolute value of electric field will be equal to magnetic field in first frame. So in first frame, so under the transformation, when you make transformation, जब आप transform करोगे इसको, so value remains. Or you can say that, so So there are many problems. So similarly, अगर हम देखेंगे अगर किसी in addition to that, if we have that electric field is greater than B in first frame, so it will be same in the another frame, right? So this will remain same. Okay. So that means by means of transformation, we can say that we can so by means of this transformation we can give any value of this E and H, but this E square minus B square remains invalid, right? Or you can have the E dot B square remains invalid, right? So we can give any value of electric or magnetic field, but provided this E square minus B square remains invalid. Okay. Now let us come back to our main topic. So that is. Uh, So we have this, we know that this action for this electromagnetic field. So this is our, so we can write now. So if you write now the action for this field, we know that, okay, let me write that. So we can write now, so we can write now this action can be written as this action of this electromagnetic field, this is minus 1 by 16 pi, yeah, km, yeah. Okay, so you can, instead of that k, you can point that I and M, so it's up to you, right? And we also know that, that E AI equal to, right? So this is our chronicle delta and this is our that field potential, right? A, right? So we can, so we have discussed in one of our lecture when we discussed that pointing vector, okay? This and this energy momentum tensor, right? So we have written that this we can write it in this form, right? And here simply that PQ dot minus L, right? Okay, so this is that classical Lagrangian we have. Okay, if you right now, if you take the variation of this now, so if you take the variation of this action, so what will be delta lambda? So that will be equal to minus 1 by 16 pi delta of, okay, or you can write this as, okay. Now we can choose here, I can write this. I will change the indices. I can, instead of this, I can write FKL will be equal to, right? So I can do this. Or if you write FKL, that will be minus term F of LK, right? If you, because this electromagnetic field tensor, it is antisymmetric. Okay. So I can, instead of this, I can rewrite this term as minus 1 by 16 pi. So I can write this as FKL. Okay, so this is simply because you can change that contra to covariant, so this will be done twice. So इसको मैंने यहाँ पे shift किया from covariant to contravariant, so this will be done twice. Okay, so this is equal to that minus 1 by 8 pi integral, that's okay. Now let's expand this. So we have this. What is this F mu here? So this F. So what's our F k here? So this will be equal to partial k partial L. Okay, so I can write this as, this will be equal to, that is partial k L minus partial L. Right, so I can write this electromagnetic field tensor in this form. Okay, right. So I can rewrite this term as then. So this term I can write as, so this will be equal to that lambda will be equal to minus 1 by 8 pi. Okay, so inside will be that it is that, so this is so, right. So I can write this as that's FKL. Okay, that's partial K AL minus partial L. तो आप यहाँ पे कहेंगे कि मैंने यहाँ पे because this was for this, so this was for that is here, right? तो अगर हम इसका covariant लिखेंगे, then this will be the covariant for partial k here minus partial n, right? So this is anything. Okay. So let us write now, because if you check now, so this is antisymmetric. This, that partial l ak, it is antisymmetric. Okay. So I can, instead of this, I can write as, this will be minus time partial k yeah, right? So because if you change the indices, so this is minus. So this you will get here twice. So you write that 2 divided by 8 pi FKL partial k. Okay. So I can rewrite this term as, so this term will be equal to, so this will be equal to, so this is minus here, sorry, so this is 1 by 4 pi FKL. This will be that partial AL by partial X, because we can write that partial K, I can write this as partial upon partial X of K, or if we have contra variant of this partial of K, so this will be equal to partial upon partial. Okay, so I can rewrite this. So instead of this, I use this one. Now let me rewrite this term. So we have this is minus here. This is our, when you take variation of this action, yeah, or this electromagnetic field. Now let us use this in our one previous equation. So our previous equation was, so if you remember that, we have that T Ki, so that's equal to partial A by partial X I into partial lambda or partial into. So ये, because I can use this, तो यहाँ से ना I can do one thing. Uh, so I can run this one. So let me write it here. So I can, instead of this, I can rewrite this term as, so I can rewrite this term as, so this will be that partial lambda upon partial AL by partial XR. So that's equal to minus 1 by 4 pi F. Okay. So I can use this in this equation. Okay. And this lambda, so this lambda we have that minus 1 by 16 pi F KL, and write any indices here. Okay. तो lambda के बदले में use करूँगा, and partial lambda by this I will use this. Okay. So let us use it here. Okay. Okay. So this term will be, so let me rewrite this term. So this will be that TKI. So this is our TKI, and instead of this I can use that. So first term will be as it is, partial A L by partial XI, and instead of इसके बदले में ये यूज करूंगा, that's minus 1 by 4 pi. Okay. And so ये हमारी फर्स्ट टर्म हो गई माइनस डेल्टा के आर, and instead of lambda you use that is minus 1 by 16 pi. Okay. FLN. Okay. Okay. So यहाँ पे why I'm using this, because why I'm not using this scale, because k is already here in delta function, right? This is our canonical delta, right? तो इसलिए मैंने इसको I can use some another indices. So instead of that k I use that ln, right? Okay. So let me rewrite this term as, so if I, so this is basically our the mixed tensor, right? Instead of that, if we change it into contravariant, so this term will be equal to, so you can add this t of ik, so that's equal to partial A by partial xi okay, so that will be partial x partial x I and this will be equal to minus 1 by 4 pi and this will be then because I am changing this into contravariant, so this will be k, right? So because here L was in covariant, here contravariant. So here I put now L in contravariant, so this will be the covariant, right? And similarly K will be the contravariant as it is, right? And I will be the covariant. Okay, so this is what we have done. And second term will be, so I can write this as instead of this G of ik. So if I change it, so we can get that because this is our that G mu nu, G mu nu, so that's equal to that 1 0 0 0. Okay. So this will be equal to, or you can write this as plus 1 by 16 pi. Okay. Right. Now this tensor it is anti-symmetric, right? So in order to make it symmetric, तो इसको symmetric बनाने के लिए, so we will add some term. So because this is anti-symmetric, so to make this tensor as symmetric, so we need to add. So we can so we need to add. So we'll add here that 1 by 4 pi. So we'll add this term. So ये term हम इसको add करेंगे, right? So in order to make this symmetric this tensor, okay? Because it's anti-symmetric. Because why we are making it symmetric? So because under transformation you can have. So when you change this in this I to k, then this will be minus. When we make it symmetric, so this will be same. So by changing this, if you change the indices, this indices, then t of ik will be equal to t ki, right? So in order to make this symmetric, we need to add this term. ये term हमें इसको add करना है. So this will be equal to then 1 by 4 pi. That's equal to f of kl, okay? And this is first term plus 1 by 4 pi partial ai by partial xn. Okay. So So this is, तो ये term हमने इसको ऐड की. So first term ये वाली term है, and second is when we add this term to this equation and plus 1 by 16 pi GIK FLM. Okay, this has it. Right. So let us write now if we combine this term. So when we combine, we will combine these two terms, right? So I can write this as, okay. So let's write that. So this term will be that 1 by 4 pi, so that's equal to, so when, तो इन दो को combine करके I can rewrite this as 1 by 4 pi and partially and both side will be f of t. Okay, तो इन दो को combine करके plus pi. Okay, so this has it. तो यहाँ पे मैंने simply इन दो को मैंने combine किया and this has it, right? तो अब हम क्या करेंगे? Let us rewrite this term as, because we know that so from Maxwell equation we can write this as we know that so from Maxwell equation, so when we write that in the coherent form, so from Maxwell equation, we have that partial k f I k equal to j of I, right? So this is our Maxwell equation, right? So when you write it in this form, now if you write that in the absence of that charge density, in the absence of if you write in the absence of charge, so in the absence of charge you can write in absence of charge, there will be no charge. अगर charge कुछ नहीं होगा. So in that case, our partial k f I k will be equal to 0, right? This will be, we can write partial f I k divided by partial x k. So that's equal to, right? So this will be equal to 0, right? So instead of that, if you convert this in that mixed tensor, so this you can write as f partial f kn divided by partial x l. So that will be equal to, right? तो ये मैं यूज करूंगा किस वाली इक्वेशन में? In this equation. So when I use this in this equation, so ये term मेरी 0 बन जाएगी, because we have that. So this term I can rewrite as, so you remember that partial f of, so this term is equal to 0, right? So I can rewrite this as so that means I can rewrite this as partial f that's equal to 0. Okay. So that is okay. So I can write this as, so this will be equal to 1 by 4 pi, and this I can write as partial FKL by partial XL AI. That's equal to 1 by 4 pi, and this term will be equal to, so because this is our that partial L AI. Okay. So this term will be 0. So using this property, so this term will be 0. We can write that TIK will be equal to, that's equal to 1 by 4 pi, and this will be our that FLI, right? And FPL plus 1 by 16 pi GIK. Okay. Right. Now, if I write now, because I can write this as FLI, I can write this as minus time F. So ये भी लिख सकते हो, because this is anti-symmetric. So if you change this indices that Li from, if I change L by I, right? So this will be minus I, right? So this uh, I can write this as, so I can write this as, what is TIK? TIK will be equal to, that's equal to, so that's equal to 1 by 4 pi minus 10 F IL LK. This is our FPL 16 pi GIK. ओके, सो दिस इज एज इट इज. तो यहाँ पे मैंने सिंपली यहाँ पे इसको मैंने रिप्लेस किया माइनस टाइम. सो दैट्स व्हाई आई पुट हियर, सो देयर इज माइनस टाइम एंड रेस्ट इज सेम, राइट? नाउ लेट अस राइट नाउ. So if I combine this equation now, okay, so I can rewrite this term as, so this T of ik will be equal to, that's equal to 1 by 4 pi. So inside will be, yeah, and this is the symmetrical. So this is symmetrical. So that means if I change the indices, I may go, if I change this I with k, so this becomes symmetrical. So that means I can prove that or T of ik is equal to, okay. Now if you calculate now, if you want to, so if you want to calculate now T of I, right? So this T of I, or you can write this as T of I, so that will be equal to 0, right? So that means if I calculate this one, so that means the sum of the diagonal elements, if you calculate the sum of diagonal elements will be equal to 0 in this case, right? And now if you calculate now, if you put that I equal to 0 and k equal to 0, so what will be T00? So we can calculate this because we have at F mu we know that, right? Because you can use this property that use the value of this electric as well as magnetic field. So because our F mu is, that is 0 minus E1, and this is E1 0. So this E1 corresponds to X component, Y component, and Z component, and similarly. And you have this B3 stands for the BZ, that component of this page, right? So अगर हम ये property use करेंगे यहाँ पे, because we have that I equal to 0 and k equal to 0. So when we substitute this and these indices are running from 0 to 3, it includes all the components. So we can find that for T00, so this will be equal to, it will be equal to 1 by 8 pi into E square plus B square. So this is nothing, this is the energy density of the electromagnetic field, right? So that means when you put that indices, like if we have this, if we have this, if we put that T33, so that means if you put I equal to 3, k equal to 3, so this will also give the same result, right? And this, if you put that T22, so this also corresponds to W. तो हर कोई जो value होगा that will be equal to the energy density of the electromagnetic field, right? Now, instead of that, if you now calculate this this T of ik, that cannot be put in the diagonal form, right? So you are basically getting that putting I equal to 0, k equal to 0, you are getting the energy density of the electromagnetic field. So maybe in next lecture we will discuss about how we can get the Maxwell stress tensor from this from this T of ik. So maybe in coming lecture we will discuss. Okay, thank you.